Hello everybody, this is a short supplementary tutorial with a couple of more examples about improper integrals in case they are of help to anyone. So the idea basically is we're trying to integrate something over an infinite region of the x-axis and try to determine whether the area enclosed could be finite, in which case the improper integral is convergent, or infinite, in which case it's divergent, or impossible to determine for some other reason. For example, it could oscillate between positive and negative values if the function continues to cross the x-axis as x heads towards infinity. So these improper integrals are sometimes convergent, which means the region that's defined has an area that's finite and can be evaluated. If they're not convergent in that sense, then they're referred to as divergent. So a couple of examples here. The first one, improper integral of x cubed from 2 to infinity. Oh, sorry, not x cubed, 1 over the square root of x cubed. And just to give ourselves a bit of context, we might think about what the picture looks like here. So the square root of x cubed is certainly positive when x is positive and heads towards infinity when x heads towards infinity. So 1 over the square root of x cubed certainly heads towards 0 as x goes to infinity. The picture is something like that. 2 is somewhere here, and we're talking about this area to the right of 2. And certainly, although its width is infinite, its height is shrinking towards 0 as x increases. So potentially, its area could be some finite value. And we know that the square root of x cubed is greater than x and less than x squared, is x to the power 3 over 2. We also know that the corresponding improper integral from 1 over x is divergent. It encloses an infinite area. And we know that the improper integral for 1 over x squared is convergent. It encloses a finite area, and this is somewhere in between those. So we can't really predict at this point whether it'll be finite or not. So the strategy for dealing with problems like this is, instead of considering the integral from 2 to infinity at the first step, take an integral from 2 to b, where we imagine b to be some point off to the right of 2, but some fixed point off to the right of 2, or some specific point off to the right of 2. Okay, so take that integral, dx. This is integral from 2 to b. 1 over x cubed is 1 over x to the 3 over 2, so it's x to the power minus 3 over 2. And just think about that as an ordinary definite integral problem. Okay, so use whatever technique is appropriate to find an antiderivative, maybe integration by parts or a substitution or whatever it might be in a different example. This particular one is a power of x, so we can integrate it just as a power of x by increasing the power by 1 from minus 3 over 2 to minus 1 over 2, and dividing by the new power. Dividing by minus a half means multiplying by minus 2, and we're evaluating that at b and at 2. So we've got minus 2 over the square root of x, minus 2 times x to the minus 1/2, evaluated at b and at 2. That's minus 2 over square root of b, minus 2 over square root of x, so plus 2 over root x. Sorry, minus 2 over the square root of 2, so plus 2 over root 2, which is plus the square root of 2. So we've got minus 2 over root b plus the square root of 2. And what that's really saying is that the integral from 2 to b is the square root of 2 minus this bit, minus 2 over square root of b, and that bit that's been subtracted off is certainly decreasing as b is increasing. So it's square root of 2 sort of minus a bit. To figure out whether the improper integral converges or not, we have to look at the limit as b goes to infinity of this expression, root 2 minus 2 over root b. So we have to ask ourselves what happens to that as b goes to infinity, whether root 2 doesn't do anything, it's just root 2, it's a constant. And the 2 over b part, 2 over root b, well, as b goes to infinity, root b is going to infinity, so this part is heading to 0 as b goes to infinity. And the limit as b goes to infinity of the expression is just the square root of 2. So our conclusion there is that the improper integral from 2 to infinity of 1 over the square root of x cubed converges, and its value is the square root of 2. Which means that the area of the region to the right of 2, enclosed under the graph y equals 1 over square root of x cubed, is the square root of 2. The area from 2 to b is the square root of 2 minus this fraction minus this 2 over root b fraction, and that bit that's been subtracted off is shrinking to 0 as b goes to infinity. Okay, so that's an example where the improper integral is convergent. And examples of this type where you're integrating 1 over a power of x over some infinite region from some fixed positive value to plus infinity, those things would be convergent if the power of x in the denominator is greater than 1. When it's equal to 1 or less than 1, it's divergent. We saw that it's divergent yesterday for 1 over x and convergent for 1 over x squared. So second example is broadly similar. We're looking at, again, over the positive x-axis from 1 to infinity, 1 over root x. So this time it's 1 over x to the 1/2. So the power of x in the denominator here is x to the 1/2, which is a lower power than x to the 1, which we know to be divergent. The picture is kind of the same, or very similar looking in its general appearance. Square root of x goes to infinity as x goes to infinity. So 1 over the square root of x goes to 0. So we're looking again at a region that sort of roughly resembles the one in the previous problem. We're starting at 1 and going to the right of 1. Okay, the square root of 1 over x is decreasing towards 0 more slowly than 1 over x to the 3 over 2 is. But the question is it decreasing quickly enough that this area enclosed is finite, or is it infinite? Can we answer this question? So the strategy is exactly the same. And I mean, having a picture in your mind like this is not necessary for tackling the problem, but it's kind of useful, I think, in having a sense of kind of, what would be a plausible answer, or what might we expect the answer to be, or how are we visualizing what it is that we're calculating here. Okay, so the strategy is the same. Look at an integral from 1 to b of 1 over root x, imagining b to be somewhere out here to the right of 1. That's an ordinary definite integral. This is integral from 1 to b of x to the minus 1/2. And again, that's a power of x. We can integrate it by increasing the power by 1 from minus 1/2 to plus 1/2 and dividing by the new power, which is dividing by 1/2. So that's multiplying by 2 from b to 1. So we've got 2 times the square root of x from b to 1. And this is 2 times the square root of b minus 2 times the square root of 1. Okay, so that's the area enclosed under this graph from 1 to b, which of course depends on b as we'd expect, but we have this explicit description of how it depends on b. To figure out what happens when b goes to infinity, when we take the integral all the way from 1 all along the entire positive real axis, we have to take a limit of this expression as b goes to infinity. Ask ourselves what happens to that when b goes to infinity. Well, this time we've got a square root of b, not in a denominator, but in a numerator. It's just 2 times the square root of b. And certainly the square root of b goes to infinity when b goes to infinity. So this expression just increases without bound as b goes to infinity. So we could note, for example, that 2b minus root 2, this goes to infinity as b goes to infinity. The limit does not exist. The improper integral is divergent. And the area in question is infinite. So the part of that that's really the answer to the question is the statement that the improper integral is divergent. Okay, in this case, it's divergent because the area of the region in question is infinite, but it's divergent because that limit doesn't exist, and we can't give a value to this improper integral. Okay, so those are a couple of sort of fairly typical examples of this type, at least, of problems on improper integrals. Thank you very much for joining me for this short supplementary tutorial. I hope that it's helpful, and see you next week. Thanks a lot, everyone.